Hello. In the last video, I began using the characteristic equation to solve a differential equation. Specifically, we solved the time-independent Schrödinger equation on the top right of your screen. And what we found is, if we defined these constants here as plus k squared, we were able to get a solution of a cos kx plus b sine kx. In other words, the solution to the time-independent Schrödinger equation here are cosines and sines. Now, of course, using Euler's equation, we could rewrite these as complex exponential functions. But the point here is, anyway, we have cos and sine. Now, in this video, what I'm going to do is, I'm going to solve the same differential equation, except I'm going to swap the signs. So I'm going to take this negative sign here and put it outside. So I'm going to swap v and e and bring the negative sign outside. So it is the same differential equation, but arranged slightly differently. And this time what we're going to find is we are going to get real exponential solutions, like this. So we will have the same differential equation, and on one hand we'll have complex exponentials or cosines and sines as the solution, and another one will have real exponentials as the solution. And this is kind of mad. It would appear that we have different solutions to the same differential equation. Now, in reality, the information which both solutions hold is the same. However, the functional form or how they look is different. And sometimes writing it in different ways allows you to actually see the physical meaning behind the solutions in a more illuminating manner. So let's get cracking. Let's solve this differential equation here, which is, of course, the time-independent Schrödinger equation. So the coefficient a is going to be 1, b is going to be 0. However, this time we're going to write the coefficient c as minus h bar squared over 2m outside of v minus e. As I said in the past video, it's not important what these terms mean for the moment. When we talk about the Schrödinger equation proper, we'll talk about the science behind the equation itself. Now we need to solve the characteristic equation. And that means we need to solve minus b outside of the square root, outside of plus or minus the square root of b squared minus 4c over 2. Now when we plug in b, we're going to get 0. And a, of course, is equal to 1. The difference between this expression and that in the previous video is we're going to have a real number inside the square root rather than a negative number. And that's simply because we've defined the differential equation differently. Now once again, I'm going to allow all of this to be written as k squared, just for simplicity. And it's k squared because we're going to take a square root anyway, so we may as well we may as well try and avoid writing square roots all the time. Now, it is very important to note that the actual value of this k and that in the previous video are clearly different. They're rearranged differently because of the minus and the plus sign. So just be careful with that. If you feel more comfortable, you could write this using a different placeholder. So I'll let you work through the steps, but this time our solution to the characteristic equation lambda is a real number. It's plus or minus k, and we have no imaginary component. In other words, beta is going to be equal to 0, whereas the last time it was basically the other way around, where the real component was 0 but the imaginary component was non-zero. So let's solve the Schrödinger equation. Let's solve the differential equation using this information. We know at this point that the most general solution to a second order linear ordinary differential equation with constant coefficients is given by this expression here, where we have a real exponential e to the alpha x, and then we have, I suppose, our complex exponential a cos beta x plus b sine beta x. And of course, alpha is the real component of our solution lambda, and beta is the imaginary component of our solution lambda. In this particular instance, lambda has a real component of plus or minus k, but it has no imaginary component. So let's plug beta is equal to 0 directly in. Of course, the sine of naught is naught. That term will disappear, and the cosine of naught is 1. So this term will disappear. Now, we'll be left, of course, with this constant a. So it appears that the solution y of x is a outside of e to the plus kx. Now, as I mentioned in a previous video, this is actually a particular solution. We need two particular solutions in order to have the general solution. So while this looks like this is the format for the most general solution, it actually only gave us a single solution. So we have to do perhaps a bit of a sleight of hand, and I'll show you that now. What we're going to do is we're also going to include the negative k solution. And we're going to take a linear combination of our particular solutions. So the first particular solution will be e to the plus kx, and the second particular solution will be e to the minus kx. And we take a linear combination by multiplying each by a constant, a and b in this case, and then basically adding them. And this is the general solution to our differential equation. Just for completeness, remember that when we had a purely imaginary solution, that was in the last video, in other words, the iota term here was non-zero and the real component was 0, it turned out that we actually didn't need the negative component. We didn't need the negative k because it gave us the same result. In this, in the current problem, however, it turns out that we need both the plus and minus solutions in order to generate a general solution which has a linear combination of two particular solutions. So what's kind of neat here is that the same differential equation written in two different ways, just by rearranging the signs and the various constants, gives us two completely different looking solutions. One has real exponential solutions, while the other has complex exponential or trigonometric solutions. Now, I can assure you that the information or the science within each of these is the same. And that actually is hidden within the k. Remember, in fact, this k and this are actually defined differently. So in fact, I probably should have k sub 1 and k sub 2 because they're actually defined differently. Of course, the constants are going to be different as well. But the form of them will be real and complex exponentials. So in reality, they look like they're completely different solutions to the same thing, but they are actually the same, or they have the same information, and that's because of the various new or differently defined constants and the differently defined wave number here, k. So you'll see when you start doing your quantum mechanics, particularly with the potential wells, that sometimes it's nice to talk about a trigonometric solution, but other times you want to look at the real exponential solution because it'll tell you about something decaying. Which you'll use will depend on your experience. So, thanks for watching. Please pass this on to your friends. Visit University Physics Tutorials for more, and happy studies.